So I'm Jaewon and working at Baidu USA. Baidu is the most popular search engine company in China. Today, my colleague Tana here and I are going to talk about our work there, autonomous driving simulation with Unity. Quick introduction of myself. Originally from South Korea, I worked at Crytek in Frankfurt am Main, Germany, and then moved to US to join Riot Games, the creator of the game League of Legends. Around 2016, I made a career switch to automotive domain, specifically autonomous driving, by joining Tesla as an autopilot simulation engineer. I'm now doing a simulation work at Baidu USA, about which I'll share more in this session.
Mine's a bit shorter. Hi, I'm Turner Sinopoli. My background's in film and animation marketing. My previous company, I worked at Lightro, where we were building light field cameras for high-end cinema and virtual reality. And from there, I transitioned to Baidu USA, where I'm the team's environment artist. We have a team of two. Kathy Fu is also in the audience, who is responsible for the visuals and the scene creation.
Thank you, Tana. In this session, I will introduce you Apollo, Baidu's open platform for autonomous vehicles. Then I'll explain what role a game engine like Unity can take in developing autonomous vehicle simulation. Most importantly, we will share our concrete work so far on perception simulation for Apollo based on Unity. I'd like to have a quick show of hands. So please raise your hand if you are currently working in automotive and self-driving space. A few, but again, as I expected, not too many. Cool, good to know. So I'd like to show you one video as a teaser before getting into the details. It well summarizes what we've achieved so far. So later I will present more about what you may have noticed from the video. Let's talk about Apollo first. I will present you its history, high-level architecture, and simulation support. Apollo provides an open, reliable, and secure software platform for its partners to develop their own autonomous driving system through on-vehicle and hardware platforms. It's the most vibrant open autonomous driving platform worldwide, with more than 309,000 lines of code, 12,000 plus GitHub stars, and 130 plus partners. It's still relatively young. The first version was released in July 2017. The latest version of 3.5 was released in January this year. From 1.0 to 3.5, we added support for different sensor configurations, such as LiDAR camera fusion setup and camera-only low-cost setup, and also new features needed for different environments, from highway to urban roads. We are still improving the existing features and adding new ones to get to the level of full autonomy in the future. As you can see, Apollo encompasses from hardware development platform, including various sensors, compute unit to real-time OS-based software platform. It provides a full-stack pipeline for autonomous driving, from perception, mapping, localization, to planning and control. On top of this, it offers high-definition map and simulation as cloud services. When it comes to simulation, it provides a sim solution for the development of autonomous vehicles with automatic grading and 3D visualization. It supports two types of simulation, a replay-based simulation called LogSim, and planning and control simulation called WorldSim. You can give it a try by visiting the linked website. As you see, the existing solution don't provide perception simulation. In this second part, I'm going to talk about how game engine can be utilized for AV simulation and some relevant challenges. At this point, it's worthwhile to mention the main purpose of simulation for autonomous driving. A simulation helps AV developers develop, test, and validate new features and improvements in a safer and more efficient way. Basically, you can cover a lot with simulation before actually hitting the road. There are different categories of simulation. First, software in the loop versus hardware in the loop. Hardware in the loop is involving an actual compute unit or even a whole car with it in the simulation, instead of using a development PC or a cluster of it on cloud. It has a benefit that it can more faithfully recreate real-world behaviors, but it's more cumbersome to use and less scalable in general. Another distinction is open loop versus closed loop. An open loop simulation is like a movie in the sense that it has no feedback loop. It just plays a predetermined sequence and cannot change in the future. Meanwhile, a closed loop simulation is like a video game. It's interactive. Algorithm decision to change speed or lanes are fed back to the simulation and affect how things unfold in the future. There is also a distinction of whether it simulates the entire AV stack end-to-end or only specific modules like a planning and control, while assuming the rest of the stack like a perception is working perfectly. Most, if not all, players in autonomous vehicle space are aware of the importance of simulation for efficient and safe development of self-driving cars. Some has their own proprietary simulation solutions, while others provide solutions that can be licensed and adapted to work with each customer's setup. There are even open source ones. Some of them use well-known game engines, and others have their own 3D rendering layers. They provide varying degrees of visual fidelity and also vary in their scene creation approaches. Some focus more on training data generation, while others focus more on online validation. At the end of the day, a simulator needs to be tightly integrated with autonomous driving software modules it simulates, such as perception, localization, and mapping, and planning and control, and with its supported hardware sensors such as camera, lidars, and radars. Therefore, using an off-the-shelf simulation might save a bit of the time in the beginning, but can limit our options and cause more headaches in the long run. That's why we developed our own simulation solution for Apollo as one of its core competencies. So what's the role of game engines in AV simulation? It enables whole-stack closed-loop simulation. It can do that by creating highly detailed 3D virtual worlds. With them, you can generate synthetic inputs to sensors like camera and lidar, photorealistic images for the former, and point cloud data for the latter. Another big upside is that you can easily output ground truth data like categories and 3D locations and extents of obstacles such as vehicles and pedestrians, and also locations of lane markers. This data is crucial for training and testing a deep learning-based perception algorithm. I'll talk more about this in the next slide. One more benefit is that you can dynamically vary the world since you have a complete control of everything in the virtual world. We will see some examples soon. The ground truth can be a foreign term to game developers. It's a term used in various fields to refer to information provided by direct observation, in other words, empirical evidence, as opposed to information provided by inference. In machine learning, you need them for supervised learning techniques, and the process of people manually tagging images or other raw data, as shown above, to provide ground truth is called labeling or annotation. Pixel level or image space annotation can be decently done manually by people, but they are not very good at guessing 3D ground truth like the depth image or 3D locations of an obstacle just from an image. So a device like a LiDAR or high-precision laser scanner is often used to obtain them in addition to manual labeling. As you can see in the images here, which are annotated data from some open data sets for autonomous driving, collecting a lot of real data a deep learning requires, and manually labeling them for ground truth can be very costly, error-prone, and time-consuming. With a game engine and highly detailed virtual world it provides, you can produce a big volume of auto-labeled data very quickly. Another benefit, a dynamic variation. You can easily change time of day. So you don't have to wait until night to test perception performance in the night, for instance. You can easily change weather too, though it may require some work to make those effects AV sensor ready, because it's not just visual effects. The performance of sensors like a camera and LiDAR needs to be properly impacted by different weather conditions. The number of vehicles and other agents on the road and their behaviors are another area you can control in the virtual world. You can also deteriorate the quality of road surface, including lane markers, using a material effect to assess perception performance on such conditions. This video demonstrates some dynamic variations we implemented. So you can see weather change from sunny to rainy, time of day, and street lamps, headlights in the night, and material effects for road degradation and wet surface. And another chart showing road degradation. Effectively using a game engine for autonomous driving has its own challenges too. The first challenge I'd like to talk about is how to efficiently create a new scene for simulation. Authoring a believable and highly detailed virtual world takes a lot of effort and time. A good tool is must, as you all know very well. For AV simulation, an efficient way to create plausible road network is crucial. It's not just about plausible loop though. You also need a way to extract topology information or HDMap data from a created road network because you need it for traffic simulation or scripting road agents. Many self-driving systems rely on the existence of HDMap data for a higher level of autonomy too. As the table shows, you may categorize scene authoring approaches by two criteria. One, whether it's a real-world replication or an imaginary creation. And the other, whether the process is manual or automated. In reality, there are spectrum on both axes. At the moment, we are relying on manual approaches in most parts, but working on increasing automation so that we can have more scalable authoring pipeline in the long run. Another challenge is high-fidelity sensor simulation. It entails photorealistic rendering for camera sensors and generating realistic point cloud data for LiDAR sensors. They affect the effectiveness of perception validation and training. Having a perfect fidelity in either is an unsolved problem at the moment. Having more sensors to simulate is going to hurt performance of simulation. So optimization is important too, as in game development. Now I'll hand it over to Turner for the last section, the middle of this presentation.
All right. Hi again. So I'm going to be talking mainly about our approach to creating the visuals. I'm going to start by briefly going over our photogrammetry pipeline. I'm going to talk about how we use Unity for photorealism, or just creating stuff that looks good. And I'll talk about our road network creation, both the tools that we use for road network creation and our approach to creating scenes for the simulator. After that, I'll hand it back to Jaewon to discuss our actual camera sensor simulation and our camera-based perception simulation. So before I get into it, I want to talk a little bit why we decided to go with Unity as our game engine. One of the biggest appeals for it was using its large ecosystem with the asset store, which allowed us to get up and running with a lot of features without having to reinvent the wheel for a lot of existing, already implemented things such as weather. We went with it because of their focus on high-fidelity graphics with their new scriptable render pipelines, and their focus on performance with their data-oriented tech stack. Another huge factor is that they've been partnering with a lot of people in the automotive industry, and they've been really great collaborators with us on this process, and they've been supporting us throughout the project. So I'll talk about our workflow for photogrammetry. Nothing we do in our pipeline is particularly unique if you're familiar with the overall pipeline. It's mainly based on Unity's expert guide that they published about a year or so ago, along with a lot of trial and error on our part for working out the best tools for our purposes. If you're not familiar, photogrammetry is the process of taking real-world objects, collecting a series of still images of the objects, and then converting that into an efficient mesh for use within real-time engines. This is our pipeline, just an overview of the software and tools that we use. For capturing our actual photographs, we use a Sony a7R III. We use that camera because it produces extremely high resolution images, and its lenses have a really nice sharpness from the middle of the still to the edges, and there's not a huge amount of distortion. We also use color charts and polarized lenses when we're shooting. For processing the actual meshes, we use a tool called Reality Capture. It's been our favorite because it's fast and it doesn't stutter when you throw 3,000 images into it and ask it to run overnight. And for building our low-resolution proxy meshes, we do it by hand in Maya, or we do it with an automated tool called Instant Meshes. For map baking, we primarily rely on XNormals. XNormals is a tool of choice because it allows you to input a super high-resolution PLY file and bake down the high-resolution detail onto your proxy. And it doesn't, again, it handles really high-resolution meshes very well. We've also experimented using Simplygon with their automated normal map baking, and Substance Designer as well. And then for cleanup, for manual cleanup, we use Substance Painter to remove any artifacts on our scans. And if we're creating a tileable texture, we'll use Substance Painter to manually fix any seams or errors with that. And then for removing the baked-in lighting data from the captured scan, we use Unity's delighting tool, which is really effective at cleaning up our scans and textures. So this is the overall process of what photogrammetry is. It starts with capturing a series of images. You move the camera in 3D space when you're taking a couple hundred pictures of an object. We use a color chart on set. This allows us to make sure we're capturing accurate texture colors, and also allows us to make sure that our photos are calibrated to each other and we have a consistency and accuracy in what we capture. The way the process works is that it takes the photos, it aligns their features, so there's a lot of overlap between each photo that you take. It aligns the features, and then because you move the camera in 3D space, it can take those two images that it aligns together and use it to create a disparity or a depth map. That depth map can be used to calculate where the camera was in 3D space, and it does this for all of the pictures that you take. It finds all of the camera positions, and then uses that to construct a point cloud of the object that you were capturing. This point cloud can then be converted into a super high resolution mesh, and then the textures are projected from the camera views back onto the geometry. It's a great way, so you capture a lot of detail. And in the mesh that you build, and also the textures that you capture. But you end up with a super duper high resolution mesh. For instance, this tree model is about 200 million polygons or somewhere around that. So it's not really Unity friendly. So the process after that is creating a low resolution proxy. For this fire hydrant, we used instant meshes, created a clean low res topology, and then we used baking tools to transfer the high frequency detail from the scan into a normal map, which we can then apply to the low resolution proxy. This allows us to create a game-ready asset that captures all the detail from the real world, but allows us to really quickly create photorealistic content a lot faster than it would be manually building. So here's just an example of the process. So you can see the source scan on the left, the low resolution proxy geometry in the middle, and then the baked maps at the end. You can see we retain a lot of the detail from the original scan, and because it's all normal map baked data, it maintains all of its interactivity. So now I'm going to talk about so that ties into our approach to building high quality images within Unity. We've achieved a result that we're happy with. So I wanted to share with you some elements that I think were essential to creating images that we think look pretty good. So the elements that we think are essential to creating good looking content, of course it is starting with real world high quality material capture. So that's the photogrammetry pipeline we just talked about. When you're starting from a real world base, then you're only building on top of a good solid structure of the real world. We use a lot of reference when we're building, of course, because we're creating simulation environments for cars that will be driving on the real roads. And then we use physically accurate lighting units and HDR tone mapping plus Unity's post-processing stack. So I'll go into each of these specifically. So we're not just building worlds that have to look good or look pretty. We're creating worlds that are training our vehicles about what real life looks like. So when we're constructing any asset inside the scene, we have to make sure that we're sourcing actual manufacturer reference, we're sourcing actual federal guidelines for how these things are constructed in real life. Not only does this make it look better because everything's proportional, when you see something with your eye, nothing stands out as unrealistic, but it also is providing valuable data for the cars so when they encounter these scenarios in real life, they're already prepared for them because we're creating them as accurately as possible. So this detail comes from either federal guidelines, such as you see on the left for how road signs are laid out, upcoming intersections, how we lay out our road markings, and then also little things like regulations on how high off of road level the streetlights need to be. But as you can imagine, as we build up bigger, more complicated scenes, things get pretty hairy in terms of how much reference you need for constructing these scenes. And you find out that the government has a regulation for absolutely everything on the road. So here's an example of a rendered image. This is just right out of Unity. And you can see, even though we used real-world material capture, with a default lighting setup, everything has a very video gamey look. It looks very CGI and rendered, and there's not a lot of realism to the image. But using proper lighting exposure, post-processing, and HDR tone mapping, we're able to create something that doesn't just look real, but looks like it was actually captured by a camera. So utilizing tone mapping, proper lighting and exposure values, and post-processing contributes to creating a high-quality image with accurate exposure desaturation, dynamic range, and contrast, which matches the visuals of a real camera. So for example, if you're exposing to the blue sky and you want a clear sky, then naturally, if you're shooting with a camera, you're going to start clipping in your darker shadow areas, which you can see here in the tree shadows on the road. So just a comparison. So all these images that we've rendered, that I've been demonstrating here, were rendered using Unity's HD render pipeline. Unfortunately, we moved away from Unity's HDRP, specifically because we were relying on Asset Store for support. While we were really happy with HDRP and allowed us to work with accurate real-world lighting values, we rely on the Asset Store for tools that increase our visual quality and add in additional features. So again, we don't have to reinvent the wheel for a weather system because somebody's already built a weather system. So we moved away from HD render pipeline, but we are planning on moving back to HD render pipeline. So the images in the demo video at the beginning were all rendered with a standard render pipeline, and then these slides I've been showing you are HD RP. Some of the tools that we do use from the Asset Store, the biggest one is Enviro. Again, it's our dynamic weather system, but it's also a time of day system. This allows us to tie in our custom effects like puddling on road surfaces and headlights and streetlights turning on and off because Enviro provides a weather system with a lot of tie-ins that we can access. We use Gaia and CTS for fast terrain and world creation, so we can sculpt terrains very quickly and then apply procedurally generated textures on top of those, which allow us to quickly get going. And we use Easy Roads 3D, and we'll get into this a little bit more, but we use Easy Roads 3D for terrain manipulation and object spawning. Obviously, Easy Roads is made for creating roads easily, but they also created a set of tools within that which allows you to do spline-based layout of objects. So any sort of roadside objects or manipulating terrain to follow our roads, Easy Roads 3D makes it really easy to access that. So we're using it kind of a way it's not intended, but these have been like the primary tools that we use, and they're awesome, and you should buy them. And of course, we've been working really closely with Unity's team. So Unity's been focusing on a lot of different verticals, especially the automotive industry, and they have a simulation team which has been providing us with a lot of support, and they also provide us with their SimViz templates. These are really great sample libraries of roads and assets that we can use, and it allows us to have a library to get started with for constructing scenes and scenarios within our simulator. It also provides base implementations of sensor simulations as reference for things like LiDAR, radar, or ultrasonic sensor simulation. So using their libraries, we were able to quickly create different scenarios and road networks to match what we were testing at the time, which makes scene creation very quick. And speaking of scene creation, now I'm going to talk about how we create our road networks. First off, I'm going to talk about the tools that we use, and then I'll discuss our actual process for building those scenarios out. Of course, when we were looking for tools to construct accurate road networks, the first thing we looked at was what do they use to design actual road networks. But looking at civil engineering packages, because they're designed for actual construction purposes, they're very heavy-handed and overly complex for what we're building. So the learning curve on those and what they provide is too much for what we're doing. On the opposite end, you have game engine plugins like Easy Road 3D, which provides you with really visually, aesthetically pleasing roads that look really good, but unfortunately, they lack the level of detail that we require for a simulation. They also require a lot of manual approaches for complex junctions, and they don't support an easy way for exporting their road topology for us to access in our simulator. We also looked at procedural pipelines using Houdini, but we didn't have anyone who knew Houdini, so we wanted to get going faster. So the tool we ended up using is called Roadrunner by Vector Zero. They've been really great to work with and collaborate with, and their tool is great because it provides a road network design and editing tool, and it also gives you lane level information and junction editing features. Most importantly, it can export an OpenDrive HD map, which we can use to import into Unity and spawn vehicles along the proper splines they should be driving on, along with all of the different scenarios that can happen in junction scenes. So you can see here an example of a scene that was created using Easy Roads. It's physically plausible, it looks good, but also every turn and intersection that you see contains the proper data that it needs. When I started, I underestimated the complexity of any simple junction, but you can see at every scenario there's a lot of different options that vehicles can drive on, and all of this gets exported to maps that we can import into our scene and spawn vehicles on. So you can see, even if things get very complex, like this roundabout here, we maintain all of the detail and information that we need to run our simulator. So that's the tools that we use. The actual process that we go through for when we're deciding what scenes to create and how to create them involves actually starting with the roads that our cars are driving on already. So we'll always start from a real-world test route, somewhere our physical vehicles are driving and learning from. We'll take those routes and reduce them into shorter, more thematically similar sections. And then we create an artificial route, which captures the complexities of the real world, but eliminates a lot of the redundant, boring parts of driving. I don't know if you've driven a car, but most of it's pretty boring. This is really important to us because we need to focus on quality over quantity, and we need to maximize our resources because we're working with an art team of 2 people, including myself. For example, if there are 2 complex intersections in a scenario that we're driving in, but they're connected by 15 miles of boring road, then we'll cut out the boring road, recreate the intersections as accurately as we can, and then use those for the simulator. And that allows us to increase the density of quality data that we're actually exporting for training and validation purposes. So I'll give you 2 examples. The first one is a 20-mile test route that our cars are actually driving on. This is in Mountain View, just south of here. As you can imagine, set decorating 20 miles of road is a pretty daunting task for a regular-sized art team, and for a tiny team, it's a big task. So what we do is we go through the actual route, we identify where the most complicated junctions, and what scenarios are we focusing on for the simulator, what data do we need to create, and then we isolate those scenes, and then construct a synthetic route that's much shorter, but content and feature dense. This is actually just photoshopped together, but you can see it's a much shorter route. It's less than 5 miles, and it allows us to focus on really fleshing out the important parts of the scene. Another example, this is another real-life test route we drive in San Mateo. This one's only 2 miles long, but you can see it's a very dense urban scene. So every mile, every couple of feet, there's a lot of detail that we need to be packing into the scenarios. So what we did was break it down into its thematically similar regions. So you can see we have a dense urban downtown section, we have a residential section, and some transition areas in between. For this scenario specifically, we actually took it and broke it down into 2 separate scenes that we wanted so that we could focus on each one and give it more time for creating a high-quality simulation environment. Here you can see the artificial route that we broke down. You can see while it doesn't match one-to-one what the real road looks like, it captures all of the important scenarios that we need to test and develop for. So you can see we have roundabouts, cul-de-sacs, we have very narrow roads. And here we broke it out into the downtown urban dense district. Again, this doesn't match the real world one-to-one, but it captures the scenarios that are present in the real world testing environment. This includes cars parked on the sides of the road, narrow streets, intersections, parking garages, and all sorts of craziness that can happen downtown. All of this work is breaking down so that we can maximize the value of every mile that we build in the simulator, and so that every frame we export contains interesting content that is valuable for the simulation teams to use for training or validation. So that's our approach to building visuals and scenes and our scenario creation. Now I'll hand it back to Jaewon and to talk about our camera simulation.
Thank you, Tana. Now let me share some details about our camera sensor simulation. To faithfully simulate a camera sensor, you need to consider its lens distortion, dynamic range, tone mapping, low light noise, and so on. This video shows a multi-camera perception simulation. You can see how it detects vehicles. The top center image shows a lane marking detections too. Visualization with concentric circles shows how it's localizing itself and other vehicles. Here are some more details on how we simulate lens distortion. The usual lenses have 2 main distortions, a radial distortion and tangential one. And the radial distortion can be barrel-shaped or pin cushion-shaped, as you can see in the images. A tangential distortion is usually much less noticeable than a radial one. There can be 2 approaches in simulating a distortion. A backward one is using inverse distortion mapping to sample proper texels in the undistorted original rendering for final distorted pixels. An alternative, which I call a forward approach, is using a 2D grid mesh, applying the undistorted original rendering as a texture to it, and distorting each grid vertex by the distortion parameters. There is a paper describing the formulas to get an inverse distortion mapping from the original distortion parameters on the Plumb model. You can find it in the reference. We are using that backward approach based on that. Keep in mind that you need to start with a bigger resolution to get a sensor resolution you need in the end, because a barrel distortion shrinks the image. For a fisheye lens, a different distortion model, such as omnidirectional model, is usually used instead of the aforementioned Plumb model. This shows a shot with different levels of radial distortion. Next, I'd like to share some details about how we implemented camera-based perception, grading, and visualization. Main detections to grade obstacles and lane markings. Detection involves 2 aspects: classification, and localization. Classification is categorizing what it sees, while localization is determining its location, first in image space and then in 3D. You probably heard about terms like true positive, false negative, and true negative. Precision, recall, F1, accuracy are values computed from those terms and often used for grading a detection performance. For grading obstacle detection, we use IOU, intersection over union, between a detected bounding box and a ground truth bounding box to determine a successful detection. For grading lane marking detection, we first regularly sample points for a detected lane line and check if a ground truth lane marking can be found within a distance to determine if the sample should be considered as a true positive. In addition to online grading, we also visualize detection result with ground truth. Implementing such visualization entails some challenges due to the asynchronous nature of the simulation. You need to cache data of last few frames to have a matching ground truth available when new perception result arrives. And for moving obstacles like vehicles, apply a delta between the obstacle transform at the time of the perception and the current obstacle transform to each detected obstacle bounding box if we want to show them in sync with the current obstacle rendering. Otherwise, they will be rendered as somehow lagging behind their corresponding vehicles. In each frame, real-time charts show grading results for the current frame with their histories, and there is the final summary at the end of the simulation run. Let's see its workings in this video. You can see the detection results and ground truth for vehicles and lane markings. Lower right sub-image shows the perspective of the sensor camera, while the main viewport shows the perspective of the viewing camera, which you can control for a better view. You can see runtime charts showing those grading metrics I mentioned, like a precision, accuracy, and so on, and also the grading summary at the end of the simulation run. With this, you can easily compare perception performance between day and night, for instance. We found out perception version we tested actually performs slightly better in the night. Let me finish with the future work. We are currently working on auto-labeled data generation for perception neural net testing and training. We need to support more sensors, including LiDAR, radar, and ultrasonic sensors. Initially, we focused on the missing part, perception simulation, but we want to provide whole stack closed-loop simulation in the end. Better traffic simulation and agent scripting is another. As the platform matures, user-friendly tools for ego vehicle configuration and scenario editing will become crucial. We also want to put it on cloud for easier and faster deployments, accessibility, and distributed simulation. So this has been a teamwork. I'd like to express my gratitude to the team members, Kathy Fu, Guo Dongrong, and Pei Tao Zhao, and also to people from departments who made this session and our booth possible. Ting Chen, Natasha D'Souza, Daming Lee, Danny Wang, Jenny Wu, and Claire Yang. Here are some references, and that's all we have today. Thank you for listening. Also, we have booths in the center hall, north of Google booth. So please pay a visit if you want to learn more. And again, as this top of the slide says, self-driving simulation has many interesting challenges that game developers like you can make an impact on. And that's the main reason we are here. So please consider that path. And also, please don't forget to fill out the survey. Your feedback is important to us. With that, any questions? So we have some swags for who ask questions like the leather mouse pad, which can do wireless charging, and some nice bags. So please, yeah, don't hesitate to ask us questions.
Hi guys, very nice talk, thank you. Can you say more words about the vehicle simulation that you're using, and kind of have you tried multiple different ones, and whether, like, what are the challenges in that area?
So by vehicle simulation, are you specifically talking about vehicle dynamics or?
Yes, like basically the tires, the wheel, is any of that important for this kind of driving, or is
Right.
it not important because you're kind of going very slowly?
Right. At the moment, we are assuming perfect control, which means, simplified dynamics. But as I mentioned, we have other simulation solution, and they recently integrated vehicle dynamics. One is the model-based, the rule-based vehicle dynamics, and they also recently looked into an integrated learning-based vehicle dynamics. So it's on our plan to integrate those two vehicle dynamics solutions to this game engine-based simulation too.
Mm-hmm. And like follow-up question, what benefits are you hoping for from doing that?
You mean by integrating the
Just
vehicle?
like what will become better if you do it? Yeah.
Basically, it will make the simulation more realistic and higher fidelity because there's a limit actual car can do physics-wise, and how abrupt turn it can make and how quickly it can brake and so on. So by introducing such vehicle dynamics model, we can more accurately simulate based on the dynamics of each vehicle we actually run.
Okay, thank you.
Sure. Kathy has it. Yeah, Kathy has it. Kathy has it. So yeah, you got the mouse pad.
Hi, thank you for the presentation. We're for NTT Docomo, and from a carrier standpoint, obviously 5G is important for us. Autonomous vehicle is important for us. Just curious from your research and work, are you guys factoring in or doing simulations of network conditions in conjunction of the image recognition, or either within Unity or outside?
Are you talking more in the context of kind of V2X?
Yeah, like within the 5G network and
I
things
see.
like that. Yeah.
So again, we have many things to do. We are not doing that kind of simulation yet, but V2X means either V2V, basically vehicle-to-vehicle communication, or V2I, vehicle-to-infrastructure communication, using 5G or other communication technique, so that each autonomous vehicle can communicate to each other to have better perception and better situational awareness. Even if some area is blind spot for me, other
Right.
cars can see them.
Yeah.
So we are aware of that, and we also we will probably work on it in the future.
Okay.
By introducing those components into our simulation, but we are not doing it yet.
Okay, great. We'll love to catch up after as well on that topic.
Cool.
Thank you.
Hello, thanks for the talk. My question is, how does your autonomous vehicle understand the virtual map? Like, what's the relation? Like, how do you connect the virtual map with the HD map?
So again, we extract road topology from the road network we create, and the Apollo platform supports different models of self-driving. There can be mainly camera-based, low-cost approach, which don't require the HD map for its working. But there are other approaches like mainly LiDAR-based, which usually require the HD map as a kind of redundancy when perception cannot see things clearly. Obviously, having HD map data for that area can be helpful. Like human drivers, if you know the way, it's usually safe for you to drive around rather than the place you first visit. So basically, those extracted HTML information, we fed back into our car software stack so that relevant module like planning and prediction and so on can use those HTML data as if they are coming from real driving case. In actual driving, those data will be also fed into using cellular connection and whatnot into the vehicle, so that the vehicle has HTML of that area. So that's how we are doing the simulation.
Okay, so a follow-up. So the simulation you showed in the presentation, they are mainly camera-based instead of LiDAR-based?
Yes. So at the moment, our initial focus was the camera-based perception simulation, but we will add LiDAR and other sensors, and in the end, the closed-loop simulation with the entire end-to-end stack.
Thank you.
Thank you.
So you touched on this a little bit during the talk, just with the art team of 2 people and going through the asset store to kind of simplify the development. Mm-hmm. But I'm curious about what size your dev team is and how long it took to get this up and running to a point where you're able to actually see impactful data for your simulation.
So we are quite small team still. We have 5 people in total. Consists of engineers and artists, and what we showed in this session is basically amount to 6 months of work of those 5 people, and we definitely want to grow because again there are still a lot of things to do to make it more useful and fully featured, and again as it becomes more mature, we need better tools, and definitely there will be more requests for different scenarios and different scenes, which requires creating more scenes. And so we are also looking into, as Turner briefly mentioned, having more automation in our authoring approach so that we can have a more scalable authoring approach in the end.
Thank you.
Thank you.
Hello, thanks for the talk. I was wondering, how do you verify that the synthetic world you create is realistic enough to exercise the autonomy stack in a way comparable to driving around the real world?
So yeah, that's actually a challenging part. So one thing we are doing is obviously the perception, which is trained on real data, is properly perceiving things in the synthetic simulation. That's kind of not really systematic, but anecdotal evidence that even with synthetic images, the perception is working as expected. But we haven't done yet, but we are going to kind of verification of simulation by, recreating some proving ground or test track in the real world in our simulation, and actually run real vehicle there, and also do simulation in that recreated simulation virtual world, and compare how car behaviors, not just perception, but other, planning and control and vehicle dynamics even. And that will give us concrete data, how faithfully we are doing simulation and what area we need to improve.
Yeah, thank you.
Thank you for the talk.
Thank you.
And my question is actually, so what's the technology reason that, because there's several different kind of game engines like Unity and Unreal, what's the reason that you pick Unity, like for example, over every other game engines?
Right. So we briefly touched some points. I actually used Unreal Engine in my previous company for this kind of simulation. But here at Baidu, we chose to use Unity. It has pros and cons. But again, as Turner mentioned, Unity has some benefit. It has a much bigger ecosystem, like a asset store and whatnot, which is beneficial, especially for a small team like us, because there are many things we can just grab and use rather than developing from scratch. And also, I personally think Unity has caught up with Unreal Engine and other high quality graphics engine when it comes to such high quality, high fidelity graphics with high definition render pipeline and photogrammetry support and so on. And also their automotive industry support was a nice bonus.
Oh, okay, awesome. So follow up is, do you get the source code of the Unity engine? So what if you want something that Unity engine normally doesn't do and you have to?
Yes, that's a good point because as you probably know, Unreal is a basically full source code access. Meanwhile, Unity, although there is a free version, source code is not accessible. So far we didn't have any need to actually look into the level of Unity source code, other than game level code we can just do in C#. Because our main, again, we are a very small team, and we currently not, we cannot afford actually, modifying the engine to have better fidelity in graphics and rendering and whatnot. But we are also willing to license even the source code access when it gets to a point we need such an access.
All right. Thank you for the answer. Yeah.
Thank you so much for the talk. Yeah, I kind of wanted to ask about Unity and modeling cameras. I'm just wondering how you found that worked, and were you able to model all the different parameters of the camera that you wanted? And I know you talked about distortion, but I'm thinking noise at night. I'm thinking different bloom effects. I'm thinking pixel aliasing, things like that.
Yes. So again, to really faithfully simulate the camera sensor, there are many things involved. We are not doing them all yet because there are as you add more and more, there's a kind of diminishing return. And even with distortion, things are already working as expected. But again, each camera sensor we has its own tone mapping behavior, which is not really well documented. And also the dynamic range is different from camera sensor to sensor. So we refer to the sensor specification to properly translate, for example, dynamic range specified in there into Unity unit, and what Unity has when it comes to dynamic range. And for tone mapping and others, we are going to actually test the sensor in the real world to get kind of table of its tone mapping behavior. And we are going to replicate, based on that table, similar behavior inside our simulation. Again, because such tone mapping details are not usually well documented. It's a kind of black box. So yeah, that's the probably approach we will take.
Okay, and to apply that behavior, are you using shaders, or how do you actually end up applying it to the camera?
Oh, yes, we are mostly using the post-processing shader effects for those things we just mentioned.
Okay, thank you so much. I appreciate it.
Thank you.
Hello. You said in the talk that the sensors performed better at night. Could you identify the reasons why that is?
We didn't do any kind of systematic research to find out the cause of it, but we have some ideas. Basically with street lamp and headlights and whatnot, things are actually clear in the night compared to the daylight scene with very bright light, sunlight coming into camera and whatnot. So that's my guess why that version of perception performed better in the night. But yeah, we didn't do any other verification why that's the case.
Thank you.
Any question? I think yeah, that's it. Again, thank you for attending.